Okay, how about this first one about cold glass condensation?
Water vapor in the air is being cooled by the cold water.
Okay, so you can say that the water gaseous is going to have more energy than the water that's in the that's on the glass. So the energy is being transferred to the glass. And what should you feel? Like, what should happen when that occurs? Say again? Yeah, that water or the glass itself will actually warm up because the energy that it takes to turn liquid water into a gas is returned to you when it goes from a gaseous phase to the liquid phase. So being in a humid environment, you might think that it was, did my water or my drink really get that warm that fast? It gets warmer faster in a wet environment than a dry environment if water is able to condense on it. Like if you were in a desert, the glass would actually get colder. Why? One, this isn't happening, right? There's no moisture in the air to actually condense on it. But then what else is going to happen if there's no moisture in the air? What's going to happen to the fluid in the glass? It'll evaporate faster in an area where there's less water. So you'll actually get more evaporation out of the glass. So you'll get less to drink, but it'll be colder, which probably isn't a good thing in a desert. But okay. So gaseous water hits the glass, gives energy to the glass, turns it into liquid. So the heat of vaporization leaves the gaseous water. So we've got a selenium dioxide, and then if it exists, draws the Vesper structure. Okay, so how many valence electrons do we have for the selenium? 6? Why'd you say 2? Did you say 2?
I was thinking the other way.
Okay. 6 here plus, times 2. So I've got 18 total electrons to deal with. Who do you want to put in the middle? Let's put the selenium in the middle. All right, so there's a selenium, and then I'll connect up some oxygens. And we've used 4 of our 18 electrons. Where do you want to put the rest of them? All right, so the oxygens are happy, but the selenium is not happy. It's still missing, right? So it's missing a lot. What do I need to do with it? Okay, so first we could put 2 electrons on the selenium, right? And that takes care of our 18, but it's still unhappy. So we could put a double bond there, and in doing so, we'll erase a couple of electrons off the oxygen. Okay, and there we go. So when I'm going to draw this thing's Lewis, there's this Lewis structure. If I want to draw its 3-dimensional and its Vesper drawing, what's the structure look like?
You keep the 2 electrons on top of it, double bonds with that oxygen.
Yeah. Because it's the only way that I can get 8 around everybody else. Where else do you want to put those 2 electrons?
Isn't that the point of the double bond?
The point of the double bond is to make sure everybody gets to see 8. So everybody is actually seeing 8 right now with that double bond. Before the double bond came in, the oxygens were good, but the selenium was still missing 2. So I pulled 2 off of one of the oxygens and turned that into a double bond. The oxygens are still seeing, 2, 4, 6, 8, and the selenium is now seeing 2, 4, 6, 8, and this other oxygen is still fine seeing 2, 4, 6, 8. If I pulled these 2 electrons off the top,
What did he see? 8 though? notice it's got double bond over there. It's got 2 double bonds over there.
That was just me. I just did that when I was trying to count up the electrons. There's only those 4 electrons and then those and those. So that oxygen's seeing 8. This guy's seeing 2, 4, 6, 8. And then the selenium's seeing 8. The selenium sees 2, 4, 6, 8. So if I take that double bond off those 2 electrons off the top of the selenium and use them to make the double bond, not good things happen. So let's do it like that. So I take the 2 that were up here and then I put them down there. Can you see why that's bad? 1, I haven't changed the number of electrons on the selenium, and 2, now the oxygen sees 10 electrons, and that's not allowed. So I drag from somebody who already, that's another way to think about it. If I'm trying to make double bonds, or I'm trying to increase the number of electrons, I have to take them away from an atom who's already seeing 8. And so the selenium can't use its to make a double bond because it's already not seeing enough. And does it matter which electrons I pick? Which lone pair? Only in the fact, as long as I'm not choosing the selenium pair. Is it like, do I use those or those or those or those or those or those? It totally doesn't matter. I mean, there's 0. It's a 1 in 6 chance that any one of those is going to end up getting used. So it's completely chaotic. It doesn't matter. So if I just pick to remove those and make a double bond there, now everybody's happy and everybody sees 8. It's really hard to see. Are we okay with everybody seeing 8 there? So what's the 3D structure look like, even though it's not technically 3D? How many things are around the selenium? 3. There's a selenium. There's a selenium, and it's got a lone pair of electrons. It's got an oxygen, and it's got an oxygen. Does it matter that the oxygen on the left had a double bond on it? It's still connected to only 3 things. So its 3-dimensional structure would show what formation? Trigonal planar. Yeah. One object can only have 3 things around it. And then what's its VSEPR structure? Just bent. Okay. Questions about that one? Okay. Pi and sigma bonds, what do you want to say about those?
Pi bonds are double bonds formed around sigma bonds.
All right. Anything else you want to say about that?
Pi bonds are on the outside, so they're reactive.
Okay.
On the inside.
All right.
Can I ask one question about the last one? About the trigonal planar and just how it has the bond with the lone pair of electrons.
Yeah, I'm just doing that so it's obvious that there's a lone pair of electrons
so
that
you
are.
could just do 2 dots. Because the line kind of confuses me. It makes me think that there's 2 more electrons. Does it matter?
I don't know. It makes it hard to see a triangle.
Okay.
But if you put, I guess if you wrote it like that and put the electrons the same distance away as the oxygens are, then okay.
Okay. Yeah.
I don't think anybody draws it like that though.
Okay.
I think everybody just, because we're not actually conserving the electrons here, are we? What I mean by that is we're not satisfying anybody's octet rule with showing those 3 lines and the 2 dots. We're still missing a whole bunch of electrons. But I get what you mean by it being a little confusing. Okay, pi bonds on the they're on the outside. What else we got? Like, what's the most important thing? most important thing is that pi bond is made from a p electron. No S characteristic is involved in that bond. There's no mixing, there's no hybridization. It's a p electron mixing with another p electron. And then the sigma bond. It's got to have an S electron. It doesn't need to be an S electron by itself, but there has to be some S involved in the mix. So down here at the bottom, we have sp3, sp2, sp. These are all sigma bonds. There's P there, but there's S. So S taints it, turning it into a sigma bond. What Alexi said about the pi bond being on the outside is important because none of the sigma bonds are on the outside. The sigma bonds electrons are located in between the atoms. Why is that important? Chemically. What do we say about the pi bonds being on the outside?
They're reactive.
They're super reactive. There's nothing protecting them. So when we're talking about an S bond or a sigma bond, we're talking about electrons that are protected from easy reactivity, that I have to use something more reactive to get access to that. So there has to be some S, and that forces the sigma bond electrons are in between atoms. So therefore they are, I don't know, protected. They're harder to react with. They're less reactive. Draw your best example of a single and double bond between two carbon atoms. Okay. So there's a single bond. That's better. Okay, so what does the sp3 hybridization shape look like?
It's a circle for the sigma, for round, and then there's 3 little teardrops.
It's a tetrahedral. So what Alexi was saying is there's a sphere, and then I'm adding these teardrop shapes. And when you mathematically add these things together, you get a tetrahedral. What's sort of missing in this sp3 thing? What could I write here that nobody does right? You could put a little 1 there. So this hybridization is composed of 1 s electron and 3 p electrons. So I have to have 4 lobes for the electrons to go to. And so that's why I've got a tetrahedral shape. So what about the sp2? What do we have there? because we've got that sphere, and we've got a pi bond, or a pi orbital, and we have another pi orbital, and that adds up to trigonal planar. Because again, one electron here, so that's only consisting of 3 electrons. And then the SP is linear because it's a sphere and 1 pi or a p orbital. So you end up basically with a bigger looking p orbital, but only 2 lobes to make bonds with. Where's the other electron? Where's the p electron from this sp2? And where are the 2 p electrons from the sp? They're off making pi bonds. So it could be 2 double bonds to the same carbon atom making a triple bond, or it could be a double bond going one direction and a double bond going in another direction. But it would have to be 2 pi bonds for the sp and 1 pi bond for the sp2. Because that other electron has got to be making a bond with somebody.